Hello, hello. Today we're going to do the side splitter theorem and the angle bisector theorem. This is going to be a great time today. So we get to mix our algebra with some of our geometry and build in some knowledge about two new theorems. First, what I'd like you to do is warm up your noggin by looking at the given diagram and write out the correct notation for the dilation that is shown that would create triangle BA prime C prime from triangle BAC. So write out the correct notation for that dilation. Because it's a dilation, we know we're going to use a D. You need to know, based on the picture that you see, where the center of dilation is. And you need to be able to determine, based on the picture you see, what the scale factor is. Then you can write your proper notation showing that it is a scale factor of 3 centered at point B. Now let's take some given lengths, knowing that our scale factor is 3. And how do we know the scale factor is 3? Well, I found the scale factor 3 because I see 1, 2, 3 compass marks extending side BA to create side BA prime. Same thing on the right-hand side. 1, 2, 3 construction arcs that would be made from a compass extending side BC to create side BC prime. If I tell you that BA is 14, BC is 10, and A prime C prime is 36, please pause the video and see if you can find the correct lengths for each of these 5 different segments. So pause the video and then come back and I'll show you if you're right. So to find BA prime, that's going to be our left side here. Because we know the scale factor is 3, we would take our scale factor of 3, multiply it times the original length of 14 to get the new length of 42. So that whole side length there would be 42 units. On the right-hand side, we can do a similar process. Take the length of BC, multiply it times our scale factor of 3, and get our new length of 30. Now, to get AA prime here, we could take the full length of 42 and subtract out the length of 14 to figure out that the length that's left is 28. But we could also use the fact that a dilation marks off the same compass size setting each time we do or use the scale factor. So when we use our compass, we are making the same size segment marks each time. So each one of those pieces between A and A prime would be a length of 14. Adding them together gives us 28. Similarly, on the right-hand side, each one of these segments here in between B to C, C to the next mark, and then that mark to C prime, each one of those is the same size, so they're each 10. Adding 10 plus 10 together, we get 20. Now, working backwards, in order to get AC from knowing A prime, C prime, because the scale factor was 3, the pre-image length AC must be multiplied times 3 to create the new length of 36. So to work backwards, we just divide by 3 to get that AC length to be 12. Now what we're going to do is take these lengths in this picture and look at different ratios and see if they are equal. So we're going to test certain proportions to see if the proportions are true or false. So each one of these diagrams here is a cut and paste of the diagrams from the top of your page. So we can use the same lengths and the same numbers to determine if the ratios are equal. So let's look at BA. BA was 14, and then BA prime was 42, so that would give us the ratio of 14 over 42. Is it equal to BC, which is 10, to BC prime, which is 30? Now, when you are testing a proportion to see if the two ratios are equal, you have 2 ways you can do it. You can go ahead and cross multiply. So if you had your calculator out, or if you used your phone, and you did 14 times 30, you would get 420. And then when you do 42 times 10, you get 420. If you cross multiply and it's the same number, then this is true. The other option, if you have your calculator with you, you can do 14 divided by 42, and that would reduce down to 1/3. And you could do 10 divided by 30, which would reduce down to 1/3, and that is also true. So that's two different ways to test to see if the proportion is true and if the ratios are equal. Now, the difference between proportion and ratio, the ratio is one individual fraction. The proportion is when the two fractions are set equal to each other. We are testing to see if these ratios are indeed equal. And for the first one, yes, they are equal. It was true. Let's try the second one. We have BA prime, which was 14, over AB, which was 12. We're trying to see if that is equal to AC prime, which is 30, over AC. Wait. I'm sorry. Let's do that part over. BA prime is 42. Man, I really screwed that up. Fixing it though. And then AB was 14. There we go. 42 over 14. And then A prime C prime was 36 over the original AC, which is 12. So we can either cross multiply or just reduce both of these fractions. 42 divided by 14 is 3. 36 divided by 12 is 3. So that one is also true. Let's move on to the third one, and hopefully I do this right the first time. So BA is 14. A to A prime was 28. And then BC was 10. Then C prime was 20. So we have BA over AA prime and BC over CC prime. If you reduce both of those fractions, or if you cross multiply, both fractions reduce down to a half, or if you decided to cross multiply, they would both cross multiply and get a result of 280. So this one is also true. Good luck with these. We're nailing all the true ones. Excuse me. All right, on to the next row. BA is 14. AC was 12. So we have 14 over 12. And then A prime was 28. And then A prime C prime, which was 36. So if we reduce those, 14 divided by 12 would reduce down to the fraction of 7 over 6. And if we reduced the 28 over 36, that would simplify down to the fraction 7 over 9. They are not equal, so that one is a false. So we cannot compare the 14 and the other partial segment with the full lengths of the side 12 and the full length of the side 36. That does not work. So why don't you pause the video and try the last two examples the same way we did the first four. Let's see what you come up with, and then come back and I'll tell you if you're right or not. So pause it, try the next two, then come back. So let's see how you did. With the first example you were supposed to do on your own, we compare the length of 14 to the length of 10 in the first ratio, and then 28 to 20 in the second ratio. If you reduced each ratio, you reduce those fractions to 7 over 5 equals 7 over 5. That works. If you cross-multiplied, you would get 280 equals 280. That also works, so that one's true. The last one, we compared the 10 to the 20. That's the partial segment BC to the side of the smaller triangle BC to the partial segment CC prime, 10 to 20. And then the full side of the triangle AC to the full side of the bigger triangle A prime C prime, 12 to 36. If you reduce the fraction, you get 1/2 does not equal 1/3. If you cross multiply, you get 240 does not equal 360. So that is false. So what we're seeing here is that we are allowed to compare the side lengths of the triangles, and they will be equal ratios. But what we did in a couple of those examples is we also compared the side split pieces. That means A and B will be in the same ratio as C to D. As long as you are using the split sides, you have to use the split sides, the pieces that are split, okay? You can set up the proportion with the parts of the split side. It does not work with the base, E and F. The side splitter only works with the split sides, not the bases. That is very important. The reason why it is that way is because the split sides were split proportionally because of the dilation, so you can compare the parts, but you cannot compare the bases. If you think back at how we started this, each one of these side sections were the same length. So I can compare the pieces of the sides to each other, but that does not work with the bases. And we showed that right here on our last example, the one you did on your own. The side of 10 and the split part of 20 does not equal the same ratio as the full base of 12 and the full base of 36. That is false. That did not work. Okay? So we cannot do that one. We cannot do that one. So let's use the ones that we can use and do some calculations. Yay! This is where we get into some algebra. So in one of our previous lessons, what we had to do was take the full length of 8 and 5 to get 13, and the full length of x and 4 to use x plus 4. What I'm saying now is we have a shortcut. As long as this side is parallel to that side, that means the bigger triangle here was created from a dilation of the smaller triangle here. And we can use the side splitter theorem and say that 8 over 5 is equal to x over 4. If we did it the big triangle way like we did before, we will get the same answer. So you cross multiply and divide by 5. All right. So why don't you try the second example here. Pause it, try it, and then come back and I'll show you. So we have 4.5 over x on the left side and 3 over 4.5 on the right side. You're going to cross multiply. You need your phone or your calculator to do 4.5 times 4.5. And then what you're going to do is divide by 3 and get 6.75 as your final answer. So hopefully you were able to do that. If I give you some numbers and say that A is 7, B is 4, D is 6, and F is 28, find C and E. Well, I can use the side splitter theorem, 7 over 4 equals C over 6, and that works just fine to get letter C. 4 times C, 7 times 6, divide by 4. I can use the side splitter theorem there because I am dealing with the partial split sides, the parts of the split sides. In order to find the bases, I have to use the full big triangle length. So I'm going to use the full length of 7 on the left over E along the bottom. But then I have to use the full length along the left of 7 plus 4. So I'm going to use the full length of 11 along the base of 28. Now you're going to cross multiply from there and solve. So we have 11e, and then you do 28 times 7, which is 196. Divide both sides by 11, and we get a repeating decimal of 17.818181 over and over and over. And that is possible, and I know it's possible because we just did it, and that's what we got. Now, this can be extended to include more than just one pair of parallel lines. In our original diagram back at the beginning, what we did is we did a dilation of 3. If I added this segment here, I would have 3 sets of parallel lines. Technically, I could see or envision 3 triangles here, all of them created using the same dilation steps, so they're all proportional to each other. So I can extend that to more proportions and more equal ratios. If I have an incomplete diagram, so the 2 lines on the side here don't actually ever meet in the picture, unlike these 2 here met at the vertex, I could still do the ratio of the pieces in between the parallel lines. So that means when I look at a diagram like this, for example 3 here, I can take the 4 and the 5, use that as one ratio, and then help me find GF by setting up a second ratio that is equal. As long as these segments are parallel, this is going to work. So I get cross multiplying here, and I get 4x equals 15, and then when I divide, I get 3.75 for GF. We can use the same ratio, 4 over 5, to help us find AG as well. So I get 4y equals 40, and then y is 10, which is the length of AG. If there's only a few parts, it makes it easier, so I can just do a over 20 equals 9 over 15. Please be careful that your a's and 9's are separated so they don't look the same. 15 times a is 15a, and then 120 times 9 is 180. Divide both sides by 15, and we get a is 12. So why don't you pause the video and try example number 5, solve for A, solve for B, and solve for C. And then if you feel it, do example 6 as well. So pause, try those, and then come back. So here we are. We could do A over 9 equals 2 over 3. Cross multiply, we get A is 6. We can take the 2 over 3 and use it in another ratio or proportion with 4 over B. Cross multiply, coincidentally get 6 again. We can take 2 over 3 and use it in a third proportion for 3 over C. Cross multiply, and we get C is 4.5. So hopefully you were able to do that and you're understanding what's going on here. For the last one, it asks you to determine if they are parallel. Now, to determine if they are parallel, what you do is you check the ratios and see if the ratios are equal. So they're telling you that EC is 2.5. So we're going to check the ratio of 1.5 to 3 and see if it is equal to the ratio of 1 to 2.5. So you can either cross multiply here or reduce the ratios. If you cross multiply, you end up with 3 is not equal to 3.75. Since the ratios are not equal, that means the parts are not proportional, and no, they are not parallel. Now we're going to move on to the other theorem, second theorem of today's lesson, the angle bisector theorem. So the angle bisector theorem says that in triangle ABC, if the angle bisector of A meets side BC at a point D, then BD, the ratio of BD to AB is equal to the ratio of CD to CA. Whew, that makes no sense. So reading it slower will make no difference at all. But let me explain, and I'll show you, and then it's actually a pretty simple thing to use. So here's why it's true. If I make a segment parallel up here, parallel to the base of the triangle, so this segment I created is going to be parallel to CB. I'm going to label the point of intersection E here. What I just created was another triangle. So I have this triangle here, and I'm going to look at what happened with this triangle and compare it to some of the other parts of our original triangle, ABC. If we look at triangle ADB, that's this one, ADB. What we see is a pair of corresponding angle or vertical angles, and then a pair of alternate interior angles. And so by the triangle angle sum theorem, the third angle of each of these two triangles would also be equal. So we have two triangles with all equal angles. When that happens, the sides are proportional. So that means that these two triangles are similar, but that's something we will discuss much more detail in a later lesson. Because these two triangles are similar, we can say that one of the triangles was created using a dilation from the other triangle, either smaller to bigger or bigger to smaller. That means we can match up the ratios of the corresponding sides. So if I compare side CD to DB, that would be in the same ratio as side CE to the base AB. Now focusing our attention next on triangle ACE, why is this triangle isosceles? Well, angle CED, this one here, is alternate interior and congruent to angle DAB. And because this whole thing started with an angle bisector, that means angle CEA will be congruent by substitution, or the transitive property, to angle CAE, creating a triangle with two congruent base angles. So by the converse isosceles triangle theorem, there also are two equal sides. That means that side AC is congruent to side EC. So then by substitution, this ratio that we did up here, CD over DB equals CE over AB, I can do a substitution in for EC, and it becomes CD over DB equals AC over AB. So in our diagram, if we look at the segments that we are dealing with here, let me clear out all of these markings and focus on our final result there. We have CD and DB and then AC, and then AB. So what's going to happen with the angle bisector theorem is we can make a proportion out of those two pieces and a proportion out of these two pieces. So the angle bisector cuts the opposite side of the triangle in equal ratios to the sides of the angle. So the angle bisector bisected angle with side AC and an angle with side AB. Those sides have equal ratios with the parts of the segment that was opposite the angle that was bisected. Now, that's the explanation behind it. Woo! Shake out your brain, shake out your hands. Let's put it to use because it actually is a lot easier than all that stuff that I just explained. Using it is easier than understanding where it came from. So look at our diagram here. Here's our picture. What we just said, or what I just explained, is that you can make a ratio 8 is to x as 12 is to y. If you'd rather, you can write it upside down compared to what I just did. And you can just say the piece over the side of the angle is equal to the piece over the side of the angle. Now in this particular problem, we have two different variables in the same proportion. So how do we find x, or how do we find y? That's where the fun algebra stuff comes into play. Because this notation here is telling us that the full length of BC is 15. So the absolute value bars around two letters is telling you that the full length of that segment, regardless of which direction you count from, is a length of 15. That means that x plus y, those two pieces, add up to be that full length of 15. So that means if I subtract y from both sides, x is the same thing as 15 minus y. We can use that in our proportion and use algebra skills to solve for y. And then once we know y, we can find x. So from here, we're going to cross multiply. You're going to distribute. You're going to add 12y to both sides. And you're going to divide by 20. And now that we know y is 9, x is 6. But the angle bisector theorem just makes a ratio out of the side of the angle and the piece attached to it, the side of the angle and the piece attached to it. So let's try another example. Example number 2, part A. We're going to make the ratio 8 over x equals 15 over y. The full length of side AB is 12. So that means for this particular example, x plus y add up to be 12. So you can solve for x or you can solve for y. It doesn't matter which one you use. If I just switch things around this time and subtract x from both sides, I get y is equal to 12 minus x. So then in my proportion, I can cross multiply. And it'll be 8y, which means 8 times 12 minus x equals 15x. If you feel like you need to see the substitution put into place, then we can do that. I would just write 8 over x equals 15 over 12 minus x. That's the substitution of the work up here, and for y there, and then cross multiply there. Sorry, I'm all over the place. Don't have a ton of room here. So go ahead and solve for x, and we'll get a decimal, 4.1739, rounded off the fourth decimal place. Bada bing. So why don't you try the next one, and we'll see how you do. So pause it, solve for x and y here, and we'll see if you get it right. So if you came up with 4.4 repeating for y and 3.5 repeating for x, then you nailed it. If you need to pause it and see why or how I got that, go right ahead. Last problem, example number 3 here, doesn't give us a diagram, so we're going to make our own. So it says the angle bisector of an angle splits the opposite side of a triangle into lengths 5 and 6. The perimeter of the triangle is 33. Find the lengths of the other two sides. So this is going to be a very similar setup to what we're doing, except for the x and the y are going to be in a different location. So I make a triangle, sketch in an angle bisector. The angle bisector of an angle splits the opposite side of the triangle into lengths 5 and 6. The perimeter of the full triangle is 33. Find the other missing sides. My proportion is going to come from x over 5 and y over 6. And then because the perimeter is 33, perimeter comes from adding all the sides of the triangle together, and that equals 33. So that means that x plus y have a sum of 22. So you can either solve for x if you want, or you can solve for y. X should be 22 minus y. Y would be 22 minus x. Use that, substitute in, pause it, solve for y, solve for x. Let's see what you do. If you did your substitution and solving right, you would get y is equal to 12, and you would get x is equal to 10. We are done with this lesson. Go do some practice. Miss you guys. Take care. Quiz is coming up soon. This is the last lesson before the quiz. Tomorrow is review, and then you'll have a quiz on forms on Wednesday the 13th. All right? So good luck. Peace out. Stay safe. Goodbye.